Now suppose that we approach Sheldrake's theory of morphic resonance as being limited by the number of steps rather than by a continuous and undifferentiated distance between an event and points of resonance. So with that approach, the comparative ease of introducing novelty during a flow experience would actually be expected. Essentially by extending the active holons along the time dimension, the distance between initial and subsequent instances of a particular pattern decreases. So an extension of holons like that necessarily includes interiority. It ensures fewer interactions with the components comprising a holon at a similar scale. And because it's interactions that lead to decoherence, an agent who experiences fewer interactions with the interior of a holon, representing some action, would expect to experience greater coherence while performing the action. And in that sense, entering flow could be thought of as working at a larger scale, although the size is only extended along the time dimension. So that model is quite consistent with both Eccles and Penrose and Hameroff's formulation. And importantly, it's pretty coherent from an intuitive perspective, so we might sum it up as follows. States only exist at the boundaries of interacting holons. In order for state to change, so we might also say in order for time to pass, regions of space-time must remain bounded. This makes them have no single state inside the boundary. That interior is a linear combination of all its possible histories. And to interact with the interior of a temporal holon is to subdivide it. Taken to its extremes, this prevents any change from taking place via the quantum Zeno effect. And the larger a four-dimensional holon is, the more potential change is possible between its bounding states and the more complex its interactions can be. And although that is consistent with established theory and it's intuitively satisfying, there are clearly some unanswered questions that could be asked about the model. For example, what, if anything, would it predict about group flow? So the boundary of an n-dimensional object has n-1 dimensions. And our default assumption when taking this approach to analyze spacetime is that we take the boundary by omitting the time dimension. And this has three-dimensional state space at either end of this boundary and four-dimensional transition amplitude in the space between. And that's similar to the model already proposed. Now, suppose we take the 3D boundary at a space rather than at a time dimension and apply it not to the mathematically approachable world of a single particles, but to our human-scaled experience. Now, at the intuitive level, that leads to some interesting images. Suppose that our boundary was the behavior of one member of a sports team during a particular play. The missing dimension might be this player's interiority. In other words, the 3D boundary could be thought of as the 2D surface of the athlete's body or sporting equipment at the time, and that plays the role of the third dimension. Now, if our hypothetical athlete is in a state of flow, then the internal state is largely left unregistered. Fewer or no snapshots of the player's internal state are being recorded in memory or oriented in narrative. And that's consistent with the practice of not judging likelihood of success or failure during an experience of doing or acting. So in that case, the only decoherence happens at the 3D surface of the athlete performing the play. And obviously, it's unpredictable what decisions the player will take during this time. Now, we might relate the tendency to cause decoherence in a team environment to friction. It seems like a very effective metaphor because of the cost of coordination, but insofar as it relates to the rate at which quantum coherence is lost via interaction with the environment, it might be very literally true, actually. If we describe friction as any interaction which raises temperature, then it stands to reason that this would be the point at which an indeterminable transition amplitude becomes a fixed boundary state. So by adding heat to the environment, any source of friction creates a lot of data about the specific interactions of the surface which caused it. Remember that term of the heat environment. And that reduces the possible internal states correspondingly. So then the practical question is, how do you reduce friction? And it seems necessary to specify the time boundary for that question to have meaning. To continue the sports example, an athlete needs to have a goal in mind, which is shared by the athlete's teammates. And achieving this goal defines the state that the team wishes to encounter at the boundary of their transition amplitude. So two general approaches to reaching a desired end state with minimal friction suggest themselves. One can reduce the difficulty of each step between the current state and the eventual target. So break a complex plan into many individual steps that are all simple to execute. Alternatively, one can reduce the number of steps between the current and the desired state. So reduce the number of steps or transition amplitudes means that each one is individually more complex and represents more total possibilities than a simpler step. And with this approach, any type of friction or noise in the data encountered has a greater chance of reducing the coherence and thus derailing the plans of the agent. So fewer possible paths to a desired end state would naturally mean a lower probability of success. But it would not be a simple matter of more paths to success equaling a corresponding higher likelihood of success. After all, a larger transition amplitude also comes with more possible routes to failure. So what seems a better description is that the more routes to success exist, the higher the likelihood of successfully following one of them across the transition amplitude to the desired boundary state. And this begs the question of how a determined athlete might, or someone like an athlete, can accomplish successful steering. And we might surmise, given the appearance of focus in so many analyses of how to successfully navigate situations like that, that the key skill may be better described as the ability to interact with potential sources of measurement so that you're not caught in a state incompatible with the desired end state. And this raises a possible contradiction in the model. So if reducing the possible paths during execution leads to desired results, then maintaining coherence across a larger holon would increase the potential routes to failure at a much faster rate than the potential routes to success. So while intuitively sensible, near-term goals are evidently easier to achieve, it would seem counterproductive to create larger holons in time for any reason. So why does flow happen? One reason our intuition in this case may not square with our experience is the quantum Zeno effect. So some minimum transition amplitude seems to be necessary for change to take place at all. And if we extrapolate from the simple example of a particle needing time unobserved in order to move a minimum distance, we can assume that larger changes between beginning and ending states would require larger, not really larger because it's time dimension, and larger refers to space dimensions, but more extreme transition amplitudes connecting the two. So retroactively, the history of the transition amplitude can be inferred, and being of a higher dimension in the boundary states, a transition amplitude can contain all the information that a series of states would, and much more. But during transition, this information can't always be allowed to propagate into the environment. So from the concept of relaxation time, the time required for a particular energy to dissipate into its surroundings, we might say that the greater a potential transition is, the more energy is required for it to take place. And extending the relaxation time of a holon is analogous to saving all this energy for a single purpose, and that allows more extreme transitions to occur. So achieving difficult transitions of state may be thought of as requiring both a clear idea of the desired end state, which while reducing the rate of energy dissipation during transition. And the less energy is dissipated into the environment, the more impressive the changes that can take place across the holon. And this transition energy makes the change possible, but it also seems to play some role in steering the movement between the desired states. So the nature of that steering will be the focus of a subsequent essay. This is the end of essay 1. I hope you found it interesting. I would, of course, appreciate any comments that the listeners would have around this theory and around the way it's been presented. And yes, stay tuned for part 2 where we talk about the nature of the transition energy and how that relates to our everyday experience.